Hi everyone, welcome to our next video in our Module 8 series. In this video, we'll be going over how to run and interpret a one-way repeated measures ANOVA in SPSS. To start off, we'll look at what our example research data we're looking at. So the purpose of the research was defined as that a researcher wants to understand how exercise might reduce the risk of heart disease by measuring concentrations of C-reactive protein, or CRP, as we will be referring to it in the rest of the video. So in here I have highlighted exercise, which is our independent variable in yellow, and then our dependent variable in green, which is concentrations of C-reactive protein, since that's what we are measuring. More into the methods, we find the researcher recruits 10 subjects to undergo a 6-month exercise training program. So again, exercise is an independent variable. And then CRP concentration is measured at 3 different stages within the 6-month period. These are now the levels of which we are tracking progress with the exercise training program, assuming that the pre-intervention measurement has 0 exercise, the 3-month measurement is with 3 months of exercise, and then the 6-month measurement with more exercise. So each one is a level of increased exercise, but they represent the different time points that we are collecting CRP concentration for individuals. The dependent variable, again, is CRP concentration. Higher concentrations are associated with a higher risk of heart disease. So the way that we get this, if you guys aren't familiar with C-reactive protein, it's a marker for chronic inflammation in the body. So higher inflammation is often associated with a higher risk of heart disease, which is how we get this relationship down here. Okay. So when we set up the ANOVA, we need to look at and make sure that our data are inserted into SPSS correctly. In here you'll see I have 3 variables: the CRP measurements for the pre-group or the pre-intervention, CRP for mid or the 3-month measurement, and CRP values for the post-measurement or the 6-month measurement. Now you'll notice that we don't have any values specified, and the reason is because of the way the data has to be set up in the data view, which we will take a look at. But when you set up repeated measures ANOVAs, all of your measures should be set to scale, because each variable or each column is representing a dependent variable measurement at a different time or under a different condition depending on what your independent variable is. So in the data view, it would look something like this, right, where each column is technically a category of our nominal independent variable. And then again, each row represents 1 subject. So the organization of this should make sense because each subject is measured 3 times. So these values in here actually represent the CRP concentrations that were measured, or the dependent variable. Once we have our data set up, we can then kind of run through our task list for running a one-way repeated measures ANOVA. Similar to last week, we are going to assume we have a normal distribution and no significant outliers of the dependent variable, specifically for each group that we are measuring. So the first step we're going to go through is setting up the test. To get to that, we do analyze, general linear model, and then repeated measures. Any of our ANOVAs that have a within subject variable will be run through the repeated measures test. So it's not just used for one-way, not just used for 2-way repeated measures ANOVAs, but we also actually will be using it for the mixed factor ANOVA that we are going to go over next week. So this is a very popular pathway. Once we get in there, we'll get a dialog box that will ask us to define our variables. So in the top box up here, we can put the factor name. So since each measurement is a different time point, this particular example was listed as time with 3 levels. the pre-measurement, the mid-measurement, and the post-measurement. Once you define your within subject factor and the number of levels, you click Add, and it will put it in this box here. Then we can add the measure name, or the dependent variable that we have measured. So CRP can go in this box. We click Add. It'll put it in this other box here. And then once we have defined our variables and our measures, we can click Define. And that will take us to the main repeated measures analog window. And this is where we're going to identify our variables. So we've got our variable list over here. And then I feel like the setup of the repeated measures test is sometimes confusing to people. So when we look at this list, I kind of have this website for layered statistics that I use gave a really nice outline of what each component of the dialog box is. So time is what is in parentheses. Okay. And 1, 2, and 3 are going to represent the levels of time. So level 1, we can say is the pre-group, so we could assign this variable here to this first level. Level 2 would be the mid-group. Again, input this one into the second spot. And then level 3 would be our post-intervention measurement. CRP is just referring to the dependent variable that you're working with. This will actually become more important when we start doing, or actually we don't do it in this class, but if you were running like a multivariate test with multiple dependent variables, or let's say you wanted to run a one-way ANOVA that had multiple dependent variables, technically it would be a bunch of separate one-way ANOVAs, but when you have multiple dependent variables, this identification portion becomes important. That way you don't end up mixing up which variables are which. But once you have these 3 input in the proper location, we can then start setting up our calculations. So the first thing we can do is set up our post hoc tests. This will be under the EM means button, so you click on that in the main window. The setup of this is very similar to how we ran our univariate test last week, or the post hocs in the univariate test last week. So you'll transfer your independent variable over to the display means for box, check the compare main effects box, and then choose the Bonferroni adjustment. From there you can click continue. It'll take you back to the main repeated measures analysis window, and then you'll click on options. Okay. So under options, we're able to select descriptive statistics as well as the estimates of effect size. Some of you might be thinking, why don't we check homogeneity tests? Because that's what we did for the univariate test. Well, because we have a within subject factor, we don't need to test homogeneity of variance. Instead, we test sphericity, which is similar but definitely different, and that is already automatically included in the repeated measures analysis. So once we click these 2, we can click continue. That'll take us back to the repeated measures dialog box. We can click OK, and then we can generate our output. So test setup is donezo. So now we have an output that we can start looking at stuff in. And the first thing we need to do is check our assumption under Mauchly's test. So again, the assumption for Mauchly's test, or the assumption that we need for any type of repeated measures ANOVA, is sphericity. Mauchly's test will have its own table as listed as Mauchly's test of sphericity, so it's pretty easy to identify. And you can see we've got some statistics in here, and then our p-value listed under the sig column. So if this value was greater than 0.05, we would say our assumption was met and then go straight to the ANOVA table. Given this example, however, our p-value is 0.043, which is less than 0.05, so that means we reject the null hypothesis. Remember, the null for sphericity is that the variances of the differences between all time points or all levels of the independent variable are equal. In this case, since we have a p-value less than 0.05, we would argue that the variances of the differences between all time points are not equal. Thus, whenever we violate sphericity, we then have to look at the epsilon value in the greenhouse geyser box. So I have this highlighted over here. Again, I put a note down here. You only look at this part if sphericity is violated. If we don't violate sphericity, everything is good, we can go straight to the ANOVA table. But in this epsilon area of our table, we're going to draw our attention to the greenhouse geyser epsilon value, which we can see is 0.648. So this isn't particularly a p-value per se, but I kept the null hypothesis here because it's related to sphericity. So again, we violated sphericity, thus we know the variances of the differences between all time points are not equal because we rejected the null. We consult this greenhouse geyser epsilon value, which if we have a value less than or equal to 0.75, we end up using the greenhouse geyser adjustment in the ANOVA table, so we know which p-value to use for the main effect. So again, because this is still part of the assumption, I just kept the interpretation and the null the same, but the actual main point of this slide is to look again at the greenhouse geyser epsilon. If it's less than or equal to 0.75, we know which adjustment to use. If, however, this value was greater than 0.75, then you would know you have to use a Hune-Felt adjustment. This will all make sense when we actually look at the ANOVA table, which is our next step to interpret the ANOVA results. So our ANOVA table is going to be listed under test of within subjects effects. I have several slides that kind of cover different scenarios. So if we have, let's say, our p-value for Mauchly's test was greater than 0.05, and we assumed that we had equal variances of the differences between all of the time points. So in other words, we said sphericity was assumed. In the ANOVA table, under our time variable, we can see we've got sphericity assumed, greenhouse geyser, Hune-Felt, and the lower bound, which was the other epsilon box value that we didn't look at. If sphericity is met, then you read the sphericity assumed p-value, which is listed here as 0.000, or as we've said in our class, we report it as p is less than 0.001. We know that's less than 0.05, so we're going to reject the null hypothesis. And the null hypothesis would have stated for the main effect of an ANOVA that exercise has no significant effect on CRP concentration, and we know CRP concentration is related to risk of heart disease, so we can add on and therefore risk of heart disease. Exercise, no significant effect on risk of heart disease. Okay. However, P was less than 0.05, so we know we can reject that statement, and we would argue or interpret our p-value as the opposite, right? So exercise does have a significant effect on CRP concentration, and therefore risk on heart disease, or risk of heart disease. Note, this is a hypothetical interpretation. Okay, so had sphericity been met, we would have used this p-value. When we violate sphericity, which was our case for this example, and the greenhouse geyser epsilon is less than or equal to 0.75, which also this example, okay, we then use the greenhouse geyser p-value, which is listed here. Okay. You'll notice that all of these p-values are the same. Not always the case. So sometimes if you guys are reporting and you write the wrong one down, it could affect your grade because you don't have the right p-value. So just make sure you're reading the table carefully. The interpretation of this p-value is the same as if we assume sphericity, though. Okay, so it's still the p-value for the main effect of the ANOVA, in which case, because p is less than 0.001, we can then interpret that exercise has a significant effect on CRP concentration. Okay, so this would actually be the result we would accept for this example, because we violated sphericity and we had a greenhouse gas or epsilon value less than or equal to 0.75. The third option that we have, and they didn't have a screenshot in the Laird Statistics website that highlighted the Huhn-Felt value, but if we violated sphericity and the greenhouse gas or epsilon was greater than 0.75, you would end up using the Huhn-Felt p-value, which is in this red box. So interpretation, again, will be exactly the same as our previous slides, where because p is less than 0.001, we can argue that we found a significant effect. So now that we know our ANOVA results, we can see if we need to run post hoc tests, which we can safely assume we need post hoc tests because we had a significant p-value under the greenhouse geyser row in our ANOVA table. So post hocs or pairwise comparisons will be our next step in the analysis. If you did not have a significant effect, your analysis is over. So you stop there. But because we had a p-value less than 0.05, we keep going. This highlighting in the pairwise comparisons table is just to reiterate the fact that your pairs are repeated twice. The way that pairs will show up in the repeated measures tests are as the level numbers that you assigned to the variables. I don't know why they don't automatically put pre, mid, and post, but for the example that we used when we set up our variables, we said that 1 was the pre-measurement, 2 was the mid-measurement, and 3 was the post-measurement. The mean difference is read very similarly to a paired t-test, so we're looking at the first column minus the second column. So that's how we get the difference between positive and negative mean differences. Our p-values are located in this column here. And from the p-values listed, ignoring the redundancies, we can find that we have significant pairs, or pairs with a p-value of less than 0.05, as between the pre-measurement and the mid-measurement, which has a p-value less than 0.001. And then we also had a significant difference between the pre-measurement and the post-measurement, which has a p-value equal to 0.001. 0.054 did not make the cut, right, because we have this other rounded value here. If you ever get a p-value that is equal to 0.05, you would just go ahead and say you have a significant effect. I've seen it some ways where if it's equal to 0.05, people don't end up reporting it as significant, just because if you're limited to how many decimal places you can report, you don't actually know if it's above 0.05 or not. So I kind of am lenient on grading because it's kind of a subjective decision, but usually if you end up with a value exactly 0.05, I highly doubt we have that in this class, but we will have scenarios like this one where we have 0.054, right, and then it's like, oh, do I round up, do I round down, what, right? So in this case, I'm going to say this is not significant because 0.054 is technically greater than 0.05. So we've identified our significant pairs, and one way we could write our interpretation is there were significant differences between pre-intervention and mid and post-intervention CRP concentrations. You could leave it at that. You could also add on, but there were also no significant differences between the mid and post interventions. because a majority of our values are significant, or because majority of our pairs are significant, you could also word this as all pairs of the time points are significant except the, mid and post-intervention measurements. So again, a lot of variability with how you can answer these, as long as you're correctly identifying the significant pairs versus the non-significant ones. Okay, so now we've taken care of our post-hocs. The last thing we're going to do is calculate our effect size. So similar to our one-way independent ANOVAs, we are going to use the omega squared effect size. Now, when we set up the test in SPSS, it will automatically give us the partial eta squared effect size, which is, there are I think there's 4 different effect sizes you can use for ANOVAs. Partial eta squared isn't typically one that is used for one-way ANOVAs, so that's why we're going to calculate the omega squared based off of our sample characteristics. So this is kind of what omega squared estimates. It's going to estimate the population effect size. I believe partial eta squared estimates variability. So again, measurements are slightly different. But omega squared is going to be calculated by taking k minus 1, where k is the number of levels of the within subject factor. That'll be multiplied by f minus 1, f being the value of the f statistic that's reported in the ANOVA table, under, of course, the appropriate correction. And then we divide that by k minus 1 times f1, so their numerator repeated, plus the product of the sample size and the number of levels we collected. Okay. So when we plug in all of our values from our research example, we end up with an omega squared of 0.63, which, according to our interpretations from last time, would be considered a large effect size. You could also interpret this as there's a large effect size between time points, or a large effect size between different amounts of exercise. Again, lots of variability interpretations. All right, so that kind of concludes all the possible scenarios or examples you might run into when you're running a one-way repeated measures ANOVA in SPSS. In our next video, we'll go over two-way repeated measures ANOVAs, which, as you guys know, two-way gets a lot more fun. So we'll revisit that in the next